Okay, so we're going to talk about chemical equilibrium, and really, chemical equilibrium is pretty much, I would say, the majority of what we're going to discuss in this class. As I mentioned before, we're going to talk about every single equilibrium that you might not even want to know about, but we will hit them all. Um, and really, when we talk about chemical equilibrium, it really does involve a certain type of chemical reaction, and you may be familiar with this type of reaction. It is one of these reactions which are essentially the ones that have arrows basically heading in both directions. And these are what are referred to as reversible reactions. And reversible reactions are reactions that basically have what are referred to as basically two directions. They have what is going from the left-hand side of the arrow are called the I was going to refer you back to the module there. Yeah, that is the reactants, and we go to the products, right, on this side here. So when we look at a reaction such as this, they have what is referred to as the forward direction. And that is when we're going, obviously, from reactants to products. And in these type of reactions, though, what can happen and what does happen, at some point, you will actually make enough products that they will decide to start reacting with each other. And when they start to react with each other, they will actually start heading in the opposite direction. And that is what is sometimes referred to as the reverse reaction. So we have a forward reaction, we have a reverse reaction. It's kind of like a two-way street, you could kind of think of it, kind of going back and forth. It will continue really to go back and forth until it reaches what is known as chemical equilibrium. And when people think about chemical equilibrium, they have oftentimes the wrong idea about what that means. It's probably because they hear equal. So they think it's equal on both sides of the arrow. And that is not actually what chemical equilibrium is really dealing with. What it is actually dealing with is rates, kinetics, like you might have talked about there in 200A. The rate of the forward reaction will eventually equal the rate of the reverse reaction. And that is basically what it means when it reaches chemical equilibrium. So what does that really mean? As we will talk about, what that really means is just as quick as those reactants make products, those guys are just going to recombine and go back the other way. So we don't end up a lot of times with equal amounts of everybody on both sides. But what that does when we do reach chemical equilibrium is essentially lock everybody into place. So it locks all the reactants into place in terms of perhaps their molarity where they're at that point, their concentration. And it also locks into place the products in terms of their concentration at that point. Because just as we lose a little bit of reactants, they pop right back the other way at the same rate. So it's basically balanced in that sense. We don't make more reactants or products. Everybody basically just maintains. We could also maintain pressures because sometimes we deal with equilibrium gases, and when we deal with gases, a lot of times we talk about pressures is involved. So that also means that if you reach chemical equilibrium, if you're dealing with a bunch of gases, what that means is when we hit that equilibrium, we will have it locked into place. The pressures will basically stay the same. They're ultimately staying the same because you're not making more or less of either of those, right? So whatever amount of gas you have causing that pressure, you have the same amount essentially. It won't change, and you'll have the same pressure that will occur. So very often when people think about chemical equilibrium, again, because they hear equal in there, they think automatically we got to have like the same amount of reactants and products, and that is not the case when we talk about reaching chemical equilibrium. Any questions on that there? So what happens when we do this? The state of the concentration of reactants and products will basically remain constant with time. Will they never change? The answer is you can make them change in a sense because you could actually do something to the equilibrium to screw it up. Yeah, so the system can be at equilibrium and then you could actually do something to it that will mess up the equilibrium. One of the nice thing about these type of reactions, or one of the interesting things about these type of reactions, is even if you try your hardest to screw it up, it will eventually find its way back to equilibrium. So it'll find its way back to the rates of the forward reaction equaling the rate of the reverse reaction. So you could have a system at equilibrium, you could do something to it to screw it up. It will then come back to equilibrium, a new equilibrium state at that point. Now, when we look at a reaction that's at equilibrium, it may appear to us if we were looking at, so for example, let's just say we had a wonderfully drawn beaker. Not too bad. There you go. So we have this wonderfully drawn beaker and this reaction, maybe it just turns reddish. That goes red. And when we look at it, it just now turned red and stays red, right? And we look at it. And to us, when we look at the beaker, doesn't look like much is going on. It looks like the reaction is over. It looks like nothing is happening. If this is a reversible reaction that has reached equilibrium, although on the macroscopic level, the big level, it looks like it's done. If you were like to super zoom in, you would see a lot of reactants going to products, a lot of products going back to reactants. There's a lot of activity happening to like keep the thing red, basically. So there's a lot of action happening, even though when you look at it, it just looks like it's done, it's over, not much is happening. So that's also something that's really important to sort of understand with equilibrium. Now, when we see equilibrium, like I said, it is static sort of in the big level, but there is a lot of activity that has to happen to maintain what is going on. Now, if we take a look at a reaction like the formation of ammonia, a little H2 plus some N2, a little NH3 action, maybe a little balancing like I'm in chemistry class, we'll do something like that, yeah. So in this particular case, when a reaction starts, a lot of times, and if you're especially starting a reaction with only reactants, so all you have is reactants, you're not have no products there, you're just basically tossing into a beaker a bunch of these reactants. Really at that point, the only way this reaction can go is forward direction or the reverse direction. If I start with only reactants, I toss them into a beaker, which reaction should actually occur here? The forward direction or the reverse direction? Yeah, all you got is reactants, right? So you got plenty of reactants. That's going to kick off basically your forward direction in this reaction basically to occur because there's no other choice, right? The availability of all your reactants are there. They're going to find each other pretty quickly because pretty much they're only the ones in the pool swimming around, right? So they're going to find each other and start reacting. And what we would see in terms of the reactants at this point is, as we can see on this graph, we will start to see our reactants starting to decrease with time, right? So in order to make products, you have to use up your reactants. So as this reaction kicks off, we'll actually start to see some decrease in our reactants. At the same time, we're actually going to start building up some products, right? We're going to start making some products at the same time. So in this case, if we only had reactants to start with, we have no products, we would basically be starting to make some products. At some point, as we start to make these products, they will be enough that they will decide, hey, let's head back this way, right? And that's what's going to kick off at some point, basically the reverse reaction to start to take place. And you could kind of see it here on the graph. You could kind of see at some point the decrease of our reactants is starting to level off, right? And we're starting to see a pretty good increase of our products as well. And that's the point where we're starting to get kind of some pushback. We're getting the reverse reaction starting to occur, right? So those guys are pushing back the other way. We're making some more reactants at this particular point. At some point, we will hit chemical equilibrium. And we could see this on the graph right around here. So we look at our reactant, we looked at our product here, we looked at our other reactant. What does all three of those lines have in common? They are all changing with time now, or are they all basically leveled off? Yeah, they all leveled off, which means is their concentration changing a lot at that point? Pretty much not changing at that point. that is when chemical equilibrium has been reached, because again, the rate at which they're going to the products will now equal the rate at which you're bouncing back the other way. And that is what I was talking about earlier, where they kind of just lock themselves in to their concentrations. At some point, when you look at this graph, it basically just flatlines, right? And that is the point really where chemical equilibrium has been reached. That's why we have the dotted line there. That's the point where all three of those in this particular example level off. At this point, they will absolutely be able to maintain that all the way through. Again, unless you do something to kind of screw it up, and they will come back to equilibrium, but they'll be able to maintain that. Any questions on that there? Yeah. So I would say in general, and again, depending on how much kinetics you talked about or not, one of the reasons for, and when we talk about kinetics, by the way, that you maybe talked about in the last semester, kinetics deals with basically the rate of a reaction. And what affects the rate of the reaction is really like the availability of reactants or products to react with each other, right? In order for some type of reaction to occur, you basically need two things to happen, as you might be familiar with. You need some type of collision, right? Before whatever is reacting, you need them to hit each other in the right location. And they also have to hit each other with the right amount of energy, which is known as the activation energy, that like hill that they have to climb to get to the other side, basically from reactants to products. So the availability of reactants in this example, for example, where we have no products, all we have is reactants, they're not going to have a very hard time to find each other, and they're going to be able to start reacting right away. Now, in the case here, if we started, for example, with all products and no reactants, we would have the reverse reaction kicking off, right? Because same situation, we basically have a lot more products. They're going to be able to find each other. And because we have no reactants, that's going to cause a reverse reaction. If we had a little bit of everybody, same sort of idea, you would have, depending on sort of which side has more, you might actually see either the reverse reaction happening faster or the forward direction happening faster. But regardless really of which one sort of starts fastest, eventually they will kind of slow down and come back to the same rate going in each direction. But the availability of reactants causes either the forward reaction or reverse reaction to go. And if you have more products, that should cause the reverse reaction to occur. Or if you infuse more reactants, it should cause the forward direction to occur. Other questions? Okay. So speaking of that, why don't we think about a reaction like this here? And initially here we have no H2 or CO2. So in this particular case, we have no products present. All we have are reactants. So again, the only option really for this reaction to happen is that forward direction, again, is going to occur because of that. Again, as that forward direction occurs, that means that we're going to initially see in this sort of reaction a decrease in the amount of reactants. We should also start to see an increase in the amount of products as this is happening. Again, at some point, we will build up enough products that they will start reacting just by the availability of them being there. And we will start to see that reverse reaction going until, again, this one reaches chemical equilibrium, which again means that rate of the forward reaction will equal the rate of the reverse reaction. And again, graphically, that is typically what we see. Anywhere where you see lines leveling out for everybody involved in the reaction, it will basically be equilibrium has reached in this type of reaction. So when we look at this reaction here, water puts a little CO, carbon monoxide, makes some H2 and some carbon dioxide. Take a moment and think about what happens in this case for everybody's concentration here. Does their concentrations go up? Do they go down? Do they stay the same? If we decided we had the system at equilibrium and we decided at this point we want to add more water to this flask. So we got everybody swimming around in the pool and we decide we want to bring more water there to it. What will happen to everybody's concentration? So take a moment and think about everybody involved. Do they go up? Do they go down? Do they stay the same? And take a moment and we'll talk about it. We'll actually talk about, there's actually a calculation that you can do that will determine, for example, it will tell you, as we'll talk about a little bit later on in this chapter, it will tell you, first off, it will tell you, is the system at equilibrium, based on the sort of concentrations that you have. And secondly, it will also tell you if it's not at equilibrium, which way it needs to go to actually make or reach equilibrium. And usually that's determined by kind of the same as earlier we were talking, in that case, you might have perhaps more products than reactants. So, you have way more products than reactants, then you probably got to hit the reverse direction to kind of balance it out a little bit. It's the rate and those type of things. So there's actually a calculation we'll do a little bit later on in this chapter that will kind of answer those questions. So let's take a look at this one here. So we have the system is at equilibrium. We decide to add more water, which is over here. So let's just talk about what should happen in terms of forward reaction, reverse reaction. If I add more water in this case, should the forward reaction or the reverse reaction take place? Probably. Yeah, that should really initiate the forward reaction as to sort of the earlier question. We now have a lot more water available, right? So our CO there, right, our carbon monoxide is not going to have to find or look around very far to find water, right? So what that's going to do is now that we have a lot more, in this case, reactants, that would definitely kick off kind of the forward direction, basically, to occur in this reaction. And because it kicks off the forward direction, this reaction, the amount of H2, should the concentration go up? Should it go down, or should it stay the same? It should go up, right? Because if we're going in the forward direction, we're making more products. So we should see the H2 concentration go up. How about the CO2? It should go up as well, right? It's also a product. How about the carbon monoxide, the CO? What should happen with that one? It should decrease, right? Because the only way to make products is we have to use both reactants in this example here, right? So we need both of those to make our products. We should actually start to see the CO go down. How about the water? What should happen with the water? Yeah, it should overall decrease, but what you would actually probably see, right, is it will actually spike up, right? And it will only spike up because you added it, right? So it definitely is going to jump up. But once you kind of artificially made it jump up, what you then should definitely see is what you said, right? It should then start reacting with the CO, and you should start to see it work its way basically back down. You may actually end up, in the case of water, more than you started with because you artificially added it. But you definitely should see it kind of peak because you added it, and then as the forward reaction is starting, it should kind of work its way kind of back down and go that way. Any questions on that? Well, that's clearly where you should lay it up.